In this video, we'll talk about how to make a mathematical model of a plant for controller design purposes. Specifically, we'll talk about modeling electrical systems like, say, a circuit made of resistors and capacitors, etc. A very important step in the design process is modeling the plants. A plant model for a dynamical system is often a differential equation, and you can write the differential equation equivalently as a transfer function from input U of s to the output Y of s. Examples of electrical systems include various circuits. For example, say the very complicated circuit system on a microcontroller used to control a motor or something else, or a simpler circuit like a filter circuit containing a resistor and a capacitor used to filter out noise from a signal. The relevant functions for electrical systems are voltages. Now remember, voltage difference between 2 points is defined as energy required to move a unit of charge, i.e. 1 coulomb of charge, from one point to another. Other relevant functions are charges, written with symbol Q, and currents, written with symbol I. Remember, current through wire is the rate at which charge is passing through it per unit time. Hence, current is the derivative of charge in that sense. To find the plant model, i.e. the plant differential equation experimentally, we can give a known input, say a known voltage, to the plant and measure the output, say the current, at various times, and then use that to find a differential equation. A differential equation which will have the measured current function as its solution for that known voltage. To find the plant model using physics, we can draw the circuit diagram and then use Kirchhoff's laws, specifically the Kirchhoff's voltage law and the current law. We may also have to use relations for resistors like Ohm's law and similar relations for capacitors, inductors, etc. Let's quickly review the Kirchhoff's laws. The Kirchhoff's current law is often written as KCL. It says that the total current entering a node is same as the total current exiting the node. Consider this circuit with many elements denoted by symbols Z1, Z2, etc. Consider a node on the top center. If 5 amperes of current goes in at that node and 3 moves on to the left, then 2 must go downwards to balance the system. Now consider a simpler node on the bottom left. If 4 ampere goes in, then 4 amperes comes out. Let me ask you a question. Can you guess what will be the current I1 as shown over here, which is entering the element Z1? Now you may think that it is 5 amperes, but not quite, because this is not a node. It may so happen that I1 is equal to 6 amperes, i.e. 6 ampere goes in and 5 amperes come out. In that case, the element Z1 must be storing the remaining quote-unquote current in it. Ultimately, the real deal behind KCL is the conservation of charge. The charge is conserved in the universe, so whatever charge flows in, same must flow out unless you're storing it. Kirchhoff's voltage law is often written as KVL. It says that the sum of voltage changes across a loop in a circuit must add up to 0. So for example, as you move along the loop as shown, let's say you start from the bottom left just below the battery. As you move up along the battery to the top, the voltage changes 5 volts. Let's say that as you move along the element Z1 to the right, the voltage decreased by 3 volts, and as you move along Z3, the voltage increased by 1 volt. Then it must be so that as you move along the element Z5 to the left, the voltage must decrease by minus 3, i.e. decrease by 3, i.e. minus 3. Thus, the sum of all the positive and negative voltages must be adding up to 0. Sum of changes being 0 means there is no overall change. Hence, KVL can be restated as voltage at a point in the loop of circuit must return to the same value as you move around and come back to the same point. Now, what is the proof of this statement? KVL is actually just energy conservation. Remember, voltage is just energy per unit charge. So all you're saying is that if you start a unit charge from a point in the circuit and get it back to the same point after moving around, you should have no net energy change. Besides KVL and KCL, we also need some other relations for electrical circuits. If we are dealing with a linear resistor, as shown by the squiggly zigzag line symbol, then you may remember the Ohm's law equation, V equal to IR. But what voltage is equal to IR? Is it the V1 before the resistor or V2 after the resistor? Actually, it's the change in voltage. Ohm's law says the change in voltage is current times the resistance. Note very carefully, it is V1 minus V2, not V2 minus V1. This is important, and it means that the voltage across the resistor decreases as you move along the direction of current, whatever you assume the current direction to be. Hence, voltage change across the resistor is negative as you move along the direction of current. This will be important for KVL applications. If you're dealing with a linear capacitor, as shown by two-plate symbol, then we have a similar relation. Voltage decreases as you move along the direction of current, and the decrease in voltage is integral of current divided by C, or charge divided by C. C is the capacitance in the units called farad. If you're dealing with a linear inductor, as shown by the curly symbol, then we have voltage decrease as you move along the direction of current, and this voltage decrease is L times the derivative of the current. L is the inductance in the units called Henry. A generic word for capacitor, resistor, or an inductor is impedance, often written with symbol Z. Note, these are not the only circuit elements. You can also have fundamentally non-linear elements, and they are very common. For example, diodes and transistors. We won't discuss them for an LTI systems class because linear time invariant system would not include those. Now, it is now time to do an example. Here's a simple circuit of two resistors, R1 and R2 in series, and we want to find the transfer function from the voltage Vin to the voltage across the second resistor. The first step is to define current. Since there's only one loop, we'll need just one current I, which is same flowing through the whole circuit as per KCL. Next step is to write voltage changes across each impedance as we move in, say, the clockwise direction of the current. Voltage drop across R1 is minus IR1, i.e. the voltage decreases. The voltage drop across R2 is minus R2, minus IR2, and the voltage actually increases across the battery by Vin as we move in the clockwise direction. Note, this all depends upon how you define your current's direction and how you are moving around in the loop. I usually choose clockwise for both of those. Also note that Vout, the output voltage, is I times R2. Next step is to write the KVL, and we can say sum of voltage changes add up to 0. So Vin minus IR1 minus IR2 is equal to 0. Now we can solve for I. And after solving for I, we can plug into Vout equal to IR2 relation to get that Vout is equal to a constant factor times Vin. This constant factor is R2 divided by R1 plus R2, and it is the transfer function from Vin to Vout. Note that this transfer function is just a number. There is no S involved. There is no Laplace transform needed because there are no derivatives. All this means that the relationship between these two voltages is not a differential equation, it's just a simple algebraic equation. As you give in Vin, you get Vout proportional to it right away-ish. There is no time dynamics involved as far as the simple day-to-day life stuff is concerned. Unless you want to go relativistic and speed of light related stuff, then there is some dynamics. By the way, this circuit is called the voltage divider circuit because the battery voltage Vin is divided into two parts across R1 and R2. We can use it to quickly reduce a given voltage, but it is not the best way for voltage conversion though, especially for high power circuits. Now let's do a more complicated example. Here is a circuit involving a resistor and inductor in series, and we want to find the transfer function from the input voltage signal to the current in the circuit. The first step is to define the current. Since there's only one loop, we'll need one current I, which is same as flowing throughout the whole circuit as per KCL. Next step is to write voltage changes across each impedance as we move in, say, the clockwise direction of the current. The voltage drop across inductor is minus L di over dt, i.e. the voltage decreases as you move from left to right. The voltage drop across R is minus IR, i.e. the voltage decreases from top to bottom, and the voltage actually increases across the battery by Vn as you move in the clockwise direction, which is from bottom to top. Next step is to write KVL. I'm writing it in a slightly rearranged form, but the gist is the same. Voltage across the battery Vn is same as sum of voltage across the resistor and inductor, which is IR and L di over dt. To find the transfer function, first we take the Laplace transform and ignore the initial conditions for current. And then we can rearrange this equation to solve for I in terms of V input. The transfer function is what you multiplied by V in to get the I. Hence, the transfer function is 1 divided by Ls plus R. Note, this is a first order differential equation and a first order transfer function. Hence, if you gave a step value of the voltage as shown, the current graph will be as shown here. It will start from 0, the initial condition, and slowly reach the particular solution, which is the steady state current. Note that in steady state, the derivative of current di over dt is equal to 0, so there is no voltage across the inductor. Hence, it is as if we just have a resistor attached to a battery, and the steady state current in that case will be V divided by R, or V in divided by R. The pole of this differential equation or transfer function is minus R by L, hence the time constant is L over R, and the settling time, i.e. the time to reach 90% of the steady state, is 4 L over R. Note further that this system is exactly same as a car moving in air with linear drag. Both are first order systems. If you compare the two equations, you shall find that inductor L acts like mass M, the resistor R acts like damping C, the current I acts like speed V, and the voltage acts like the force F. This analogy between the electrical and mechanical systems is very deep and interesting. You can make an electrical circuit that will behave exactly as a combination of spring mass and damper systems. Finally, let's do an example with two loops. Here's a circuit that has a capacitor, inductor, and a resistor, and we want to find the transfer function from the applied voltage V in to the voltage across the resistor R. The first step is to define current. Since there are two loops, we need two currents, I1 and I2. Note that I1 flows in the battery and the capacitor. It splits into two parts, and I2 goes into the resistor R, and I1 minus I2 goes down in the inductor as per KCL. After that, the inductor current combines with the resistor current to once again produce I1, which flows into the negative terminal of the battery. The next step is to write voltage changes across each impedance as we move in, say, the clockwise direction of the current in each loop. Voltage drop across inductor L is minus L di2 minus I1 over dt. The voltage decreases downwards as you move along the inductor. The voltage drop across R, the resistor, is minus I2 times R as you move rightward. The voltage drop across the capacitor as you move rightward is integral of I1 divided by C with a negative sign due to the decrease. Note, this all depends upon how you define your current's direction and how you're moving around in the loop, clockwise or counterclockwise. I usually choose clockwise for both. Also note that the output voltage Vout is I2 times R. We are concerned with the magnitude of V out. Next step is to write the KVL, and we'll have one for each loop. For the first loop, as shown over here, we have V in minus voltage drop for the capacitor minus voltage drop for the inductor is equal to 0. Next step is to take the Laplace to get rid of the integral and the derivative. Remember, integration in time domain is same as division by s in the s domain, and differentiation is basically multiplication by s, ignoring the initial conditions, of course. We can similarly write KVL for the second loop as shown. Let's start from the left of the resistor. As we move right, the voltage decreases by I2 times R, and hence the negative sign, but as we move in the counterclockwise direction of the loop, we'll have to move up the inductor. And we know that the voltage decreases downwards as per the current we chose. Hence, the change in voltage is positive across the inductor as we move in the counterclockwise direction. The clockwise direction. This is how we get the KVL as minus I2R plus L times the derivative of I1 minus I2. There are other approaches too. For example, you can Maxwell's loop currents and things like that. The next step is to take the Laplace, and we get a cleaner looking equation like this. Now that we have two KVL equations in the S domain, we can solve them together to get I2 by a lot of algebra. And this I2, when plugged in the relationship V out equal to I2R, can be reworked into V out is some function of S times V in, and this is how you get the transfer function. Finally, note one thing. We always end up taking Laplace. So why don't we just skip a step and just take Laplace of the resistor, capacitor, and inductor relationships. We'll get V equal to I times R for resistor, V equal to I times 1 divided by CS for capacitor, and V equal to I times LS for inductor. Hence, in the S domain, all three linear elements have equations very similar to the Ohm's law, V equal to I times R. And the generic word for all three elements or their combinations is the impedance. The impedance for a capacitor is 1 over CS. Impedance of an inductor is Ls, and impedance of a resistor is R.